Hi everybody, this is Mr. Nolan, and what I would like to do with you in this video is to quickly go through the mathematics of bacterial reproduction. I'm confident that you guys understand the math. It's just a matter of what logic is going on here. So we've got two goals in this video. One is to be able to calculate the number of bacteria after a certain amount of time has passed, and that's quite easy. So we'll do one quick, simple example. And then sort of the more complicated example, we want to be able to calculate how do antibiotics influence the growth of bacteria. We saw that in the web lab and some of the other videos, but we didn't really look at the actual math. So first, let's hit this first goal, calculating how many bacteria there are after a certain amount of time. This is pretty easy, so I'll give you a pretty easy example. Suppose you eat an egg, and this egg is cooked improperly, and it's got salmonella, because everybody knows that's the big germ that you can get from eggs that aren't cooked right. The bacteria reproduce once every 3 hours. How many bacteria will there be after 21 hours? So you can see there's three numbers here. There's 93, that's the number of cells we start with. There's 3 hours, every 3 hours, and then we want to know after 21 hours, how many are there? So there's a handful of numbers here that we need to interpret. So the important thing is to recognize I've already set up the table for you in such a way that I've arranged it so that each unit of time is one reproduction. They reproduce one time every 3 hours. That's why on the table I didn't say hours 0, 1, 2, 3, 4, 5, 6, and so on. I skipped 3 hours. Because what we're really interested in, we're not interested in the amount of time that passes, we're interested in how many reproductions are happening. So I'm going to walk over to the board, so my voice might get a little quiet here. But really, the idea is that from 0 hours to 3 hours, this is one reproduction. One time that the cells are reproducing. And then from 3 hours to 6 hours, that's another one time that they're reproducing. From 6 to 9, from 9 to 12, from 12 to 15, and then to 18 and 21. Each one of these is just one round of reproduction. So what's important here is to recognize, well, what is the math that happens from one round to another? So if I've got, each hour or each 3 hours is one round of reproduction because the bacteria reproduce once every 3 hours, what's the math there? And the way that math works is that my 93 bacteria, because they're all reproducing, they're just going to double. That's all. They just double. So it goes from 93 to whatever 93 times 2 is, okay? So we're going to go from 93 to 93 times 2. That's what's going to go in the other part of the table. And so that's going to give us 186. What that means is that our bacteria reproduced from 93 to 186 because their number doubled. Their number doubled, they reproduced one time over these 3 hours, and that's why we doubled it. We multiplied it by 2. So take a quick moment, maybe take a piece of scratch paper, and go ahead and do all of the 3-hour increments all the way up to 21 and see if you can't calculate how many bacteria there will be after that time. I'm going to pause the video and give you a moment in order to do that. So go ahead. So you can pause and go ahead and do the math, and then we'll check. You can check your math against mine. So go ahead and pause things. Okay, so hopefully you've had a chance to do the math. I'll do it up on the board with you really quickly. So we just have to double every time. So the 186, when I double that, I'm going to get 372, right? My 186, so after 6 hours, I have 372 bacteria. And then after another 3 hours, it's going to increase to 744, because that multiplied by 2. If I multiply that by 2 again, I'm going to end up with 1488 after 12 hours. And if I multiply again, I'm going to end up with 2976. If I multiply that again, I'm going to end up with 5952. If I multiply by that again, I'm going to end up with 11,904 cells. So this is how many bacterial cells there's going to be after 21 hours. I just doubled it every 3 hours. And once again, I can't emphasize enough. It doesn't matter how many hours pass. What matters is how many reproductions occur. That's when you multiply by 2. It's not every hour, it's every 3 hours. So I'm going to sketch a graph up here really quickly, just so that you can kind of see what would this look like if it was all scaled properly. Okay, so this is a little smushed here. So you can see I topped it out at 12,000 because we're ending just a little under 12,000. On the bottom, I tried to space the hours as cleanly as I could, so we ended with 21. And I just put a dot here, right? And you can see this nice clean sort of slide. This is our exponential slide. And last thing we just have to do is just connect all the dots. And we have our nice, beautiful exponential graph, our J-curve or our exponential slide. So this is what our bacteria are doing over time, as long as they are able to reproduce and there's no interruptions. So I'm sorry for the mess over here, but I think that you probably get the mathematical logic. Just most important thing, don't worry about how many hours, it's how many reproductions, right? It's how long it takes them between reproductions that helps you to figure out how many times do I multiply that by 2. Okay, let's jump back to our goals here. So we've pretty much done this one. So be able to calculate the number of bacteria after a certain amount of time has passed. We're pretty much done with that one. So that's a big check mark right there. Oops. Okay, so we're done with that one. Now we want to be able to calculate how antibiotics influence the growth of bacteria. That's our next goal. So this example is a little more complicated. So you have to kind of follow the math with me here. So it works the same way at first. Suppose you have a staph infection and there's 17 cells. It reproduces 1 time every hour, so it's going to reproduce a little faster. And as a result, I've also created the table in that way. It goes by 1 hour, whereas over here it was every 3 hours, right? Here it's every hour. You take an antibiotic every 3 hours, and it kills most of the bacteria, 83%. How does the population change over time? So first, there's no dosing at first, right? So you don't take any antibiotics for a while. But let's go ahead and just calculate these first few numbers, and then we'll talk about what we do once we get to a dose. So we want to figure out, well, what is our bacteria population going to do over time? So like I talked to you in the previous example, it reproduces 1 time every hour, right? That's the important unit of time there, once every hour. So between hour 0 and hour 1, what math do I have to do in order to get from 17 to the next hour? What math do I have to do there? Do you remember? That math that I have to do is times 2. So let's go ahead and do all that math on the board really quickly. I'm going to start off with 17. If I multiply that by 2, I get 34. If I multiply that by 2, I get 68. And if I multiply that by 2, I get 136. This is where things get a little bit more complicated, because if you just multiply by 2, then you're ignoring the dose. So what we have to do is do a little bit of math to show, well, what do we end up with here once we dose with the antibiotic? The key number is 83%. And so this is what's so important. That 83%, if it kills 83%, what we really need to know is who are the survivors. Because remember, in our model, it's those survivors that are important. And so if I kill 83%, what is the percent of the survivors? Can you do that math really quick? Because you're going to have to be able to. If it kills 83%, what percent survives? Take a quick second, see if you can't do that math in your head. And time's up. If you kill 83%, that means that 17% survive. So 17% survive. And remember, you're going to turn that percent into a decimal, because all percents are really just decimals of 1. So the 17%, the best way to really write that is 0.17. That's how many actually survive. 83% die. So this is where the funny math comes in. I have to take my 136 bacteria right here, and I have to multiply that number by 17%, that 0.17, because that's how many are going to survive after a dosing. So if I take my 136 times the survivors, 0.17, I get 23 and some change. Now, I'm going to round that to the nearest whole number, because you can't have half a cell or a part of a cell. So I'm going to actually round that to the nearest number. That's why I get a 23. But now, the bacteria are going to start reproducing again. Those 23 survivors are going to start reproducing. So now what math is going to happen? It's just times 2, right? It's times 2. So my 23 times 2 is going to give me 46. And my 46 times 2 is going to give me 92. My 92 times 2 is going to give me 184. But now here we have to stop again because my 184 is going to get dosed because it says so. And it's going to kill all but 17%. So now when we do that, we're going to say there's only 31 and some change left. So I'm going to round that to 31. But now the bacteria are going to start reproducing again. So multiply that by 2. So 31 times 2 is 62. 62 times 2 is 124. And then 124 times 2 is 248. So if you did all the math right, you should end up, I know it seems a little bit hairy, a little bit complicated because we're throwing in this times 0.17, but that's the percent that survives. That's what we found over here. So let's go, I'm going to go ahead and graph this on the best scales that I can, and we'll take a look at what that pattern looks like and also what it means. Okay, so I've gone ahead and graphed this. That's bacteria on the left and time on the bottom. And I just realized I made a small mistake here, so sorry. But we're going to go from 6 to dose, and then this should actually say 7. It doesn't change any of our math. It just changes how high we can go up to. So in this case, we can only go up to 9 hours, so we don't have to go all the way up to 10. This should hopefully, I hope that this can kind of illustrate what's going on. As we watch here, this sort of sawtooth pattern, what we find is the bacteria have an exponential growth. They increase and increase. And then there's a big drop when we get that first dose of antibiotic. And there's only 23 survivors. And as those increase and increase, notice it gets higher. It actually peaks higher than it did before. You take the antibiotic, there's a big drop. But it doesn't drop as low, right? It's actually a little higher than it was before. It went from 23 to 31, right? 23 a minimum, 31 to minimum. And now it starts to increase even faster because you already start with more bacteria. So the sawtooth pattern, almost like you're looking at the side of a Christmas tree, this is how bacteria become resistant. This is sort of part of our model. Basically, you know, this is when the green is when Addie starts to feel sicker and sicker, right? We talked about the Addie situation. And blue is when she's taking a new antibiotic. So she takes a new antibiotic, she feels better. Then here she feels sicker and sicker, and then she feels better, takes a new antibiotic, gets sicker and sicker and sicker. Of course, in Addie's situation, this process took place over several weeks and months. We're just kind of taking an example over a few hours, but you can relate this to Addie. Gets sicker, feels better, gets sicker, feels better, gets sicker. And so this process over time can result in pretty much all antibiotic-resistant bacteria, which we actually saw in a previous video about our antibiotic resistance model. So I'm hoping that this kind of helps to take a little bit of the anxiety out of how to do this. This is the strategy. You just double it unless you dose, and then you're going to multiply by that percentage of survivors. But now at this point, we should be able to do our second goal here, of being able to calculate how antibiotics influence the growth of bacteria. So that one's a big check mark also. I hope that this was informative and helpful and that you can use it for studying for the test.